So in the next unit, stability. So stability analysis in S domain. So here we'll be discussing concept of stability, root stability criteria, qualitative stability, and conditional stability, limitations of root stability, and followed by the root locus technique and the root locus concept, its construction, and effects of adding poles and zeros to the g of s, h of s in the root loci. So here basically stability, so it can be defined as a linear time invariant system is said to be stable if the bounded output is obtained for a bounded input. That is called a stable system. So here in a linear time invariant system, a linear time invariant system is said to be stable, if bounded output is obtained for a bounded input. So this can be called as a BIBO system, BIBO stability, bounded input, bounded output. So that can be called as a stable system. So we need to get a bounded output as and when we apply a bounded input. So that system can be called as a stable system. And an unstable system, in the process of giving this bounded output, it will be breakdown. So it will just breaks down. So in the process of giving this bounded output for an unstable system, it will breaks down. So here the impulse response of the system must approaches to 0 as the time t tends to infinity, then the system also called as a stable system. So this is another definition. The impulse response, generally the transfer function can be called as the impulse response. The impulse response of the system, must approaches to 0 as time t tends to infinity. As the time constant, that as the time in the x-axis it reaches to infinity, the impulse response of the system must approaches to 0. Then that system is called a stable system. Then the system is called a stable system. So these are the two definitions of stable systems. The impulse response of a system to be stable, it must absolutely integrable between the limits 0 and infinity. Then that system can be called as a stable system. So if the impulse response of a system to be stable, so it must absolutely integrable between the limits 0 and infinity. So that is one of the condition. The impulse response of a system to be stable, it must absolutely integrable between the limits 0 and infinity. If it is integrable between 0 and infinity, then the system will be definitely stable system only. Next, conditions for the stability. Conditions for the stability. Let us see what are the conditions are required for a stable system. So first one is, so generally before discussing the conditions of the stability, let us see the S plane. S plane is nothing but sigma j omega plane. So this is minus sigma minus j omega, called S plane. So here this is the origin, and this is left hand side of the S plane, this is the right hand side of the S plane. So this is the imaginary axis, Right. Now, first condition is, for a system to be stable, all the poles of the system must lie in the left side of this S plane. All the poles must lie in the left side of the S plane, then the system can be called as stable system. So, this area is called stable area. And if one of the pole, if at least one of the pole is lying on the right side, then this system is called unstable system. At least one pole is lying on the right side of the system, right side of the S plane, this can be called as unstable system. So, at least one pole is lying on the imaginary axis. This this system can be called as marginally stable system. Marginally stable system. So, therefore, here for a system to be stable, all the poles, not even single pole, all the poles of the system must lie in the left side of the S plane, in the left hand side of the S plane, then the system can be called as stable system. Or in other words, we can say like the poles must have negative real parts. The poles must have negative real poles, negative real parts. So both ways we can tell this one. So for a system to be stable, all the poles of the system must lie on the left side of the S plane, so that can be a stable system. If at least one pole is lying on the right side of the S plane, that can be called as an unstable system. And at least one pole is lying on the imaginary axis, that can be called as a marginally stable system. Let us define what is the pole and what is the zero. So let us define pole. It is the negative inverse of time constant at which the magnitude of the transfer function is infinity. It is the negative inverse of time constant at which the magnitude of the transfer function is infinity. Magnitude of the transfer function is infinity. This is called the pole of a transfer function. And similarly, zero, it is a negative inverse of time constant at which the transfer function of the system is 0. It is the negative inverse of time constant at which transfer function of the system is 0. Transfer function of the system is 0. So here the time constant can be defined as, next one is the time constant. So how can you calculate the time constant means? So for example, we are having number of poles. There are two types of the poles. One is dominant poles and another one is insignificant poles. So the dominant pole is nothing but the pole which is located near to the origin is called a dominant pole. So this is the origin. So let me take, so these are the poles like this, and so these are the poles we are having. So in this, the dominant pole is this one, and the poles which are lying far away from the origin are called insignificant poles. and this is the dominant pole which is near to the origin. So here the time constant can be calculated as it is the negative inverse of the dominant pole in S plane. So it is the negative inverse of dominant pole in S plane. Dominant pole in S plane is called the time constant. So this is the S plane, sigma j omega plane. So here this is the time constant. So let me take one example to explain this one. So here this is the S plane. Let me take sigma j omega plane, and here there is a pole minus 0.02 and there is a pole minus 0.03. So here the time constant can be calculated as dominant pole is 0.2, so therefore this is negative inverse of dominant pole, so this will be 5 seconds. So that's why you can calculate the time constant. So this is the dominant pole region, so which are very nearer to the origin can be called as the dominant pole region. So this is the dominant pole region. Dominant region example. So for example, if you are having complex conjugate poles like this, let me take one pole is minus 6 and another pole is minus 5 plus or minus j3. So here this is minus 5, let me take this is j3 and this is minus j3. So one pole is located here and another pole is located here. So here that means minus 5 plus or minus j3. So one pole is located here, another pole is located here, and here another pole. So there are 3 poles, let me take. So here in this case the time constant will be minus of minus 1 by 5. So this means 0.2 second. So here this is the negative axis. So here minus 5 is the dominant pole region. So therefore you have to take dominant pole region as a time constant. Tau is equal to minus 1 by minus 5, which is nothing but 0.2 seconds. So after that, second one, marginally stable, or limited stable, or just stable, or critical stable. All are having same meaning only. Critical stable. We are saying marginally stable or limited stable or just stable or critical stable is nothing but the same only. So the impulse response of the system is said to be marginally stable if it has a fixed magnitude and oscillations then when the time t tends to infinity. So it should have non-repeated poles on the j omega axis and origin. And if the system is having repeated poles at the origin or j omega axis, then the system will become unstable. The system or the impulse response, of a system is said to be marginally stable. If it has fixed magnitude and oscillations. When the time t tends to infinity. It should have at least whenever we are having poles on the imaginary axis, there are two cases, like it may be at origin or somewhere in the imaginary axis. So this type of system can be called as marginally stable, which is having fixed magnitude and as well as oscillations. There should not be any repeated roots. If any repeated root is available, then the system becomes unstable. If repeated roots are available on j omega axis, then the system becomes unstable. So there should not be any repeated poles on the imaginary axis. If there are repeated poles on the imaginary axis, then the system will be unstable. Example we'll see for a transfer function having 1 by s into s square plus 4 into s plus 1. So one transfer function, and another transfer function is having like this 1 by s square into s square plus 4 into s plus 1. So in these two cases, let us take for this one in an S plane, s is equal to 0 is one pole and s square plus 4 is there. That means plus or minus 2j, another two roots, and s plus 1, that means s is equal to minus 1. So total 1, 2, 3, 4. 4 roots are there. So 4 poles are located. So from this diagram, it is clearly observed that there are no repeated roots on the imaginary axis, no repeated roots on j omega axis, and no single pole on right hand side of the S plane. So the system is marginally stable. Marginally stable. Marginally stable system. If you take this, there are two roots are available on the origin s square. Two roots are there, that means it is a repeated root. So directly we can say that the system is unstable system. Unstable system. Next, conditionally stable. It depends upon the gain k. If a system is stable for every value of gain k, then the system is called always stable system. If the system is stable for only certain values of gain k, then that system is called conditionally stable system. Let me take the system like k into s plus z1 into s plus z2 so on divided by s plus p1 into s plus p2 into so on. Here this is the feedback. I am just taking unity feedback system. This is R of s and this is C of s. So here the value is mentioned like 0k, which is lying between infinity, or something like 0k between 20. So like this is depending upon the gain k. It completely depending upon the gain k. If the system is stable for all the values of gain k, so this is called always stable system. If the system is stable for only certain values of the gain k, then the system is called conditionally stable system. So most of the practical systems are conditionally stable systems only. So here I can write like this. This conditionally stable system is completely depending upon gain k, depending upon gain k of the transfer function. If a system is stable for every value of gain k, then the system is called always stable system. Or if a system is stable for certain values of gain, if the system is stable for certain values of gain k, then this can be called as, in this case, the system is conditionally stable system. Conditionally stable system. So most of the practical systems are conditionally stable systems only. Most of the practical systems are Most of the practical systems are conditionally stable system. Conditionally stable. Next one is absolute stability. Absolute stability. And later we are also having relative stability. Relative stability. So here absolute stability means it gives the yes or no information regarding the stability of a system. It will gives only yes or no information of the stability. Yes or no information. Information of the system. Yes or no information of the stability of a system. Stability of the system. That means whether the system is stable or not, we can know by using this absolute stability. So example for this is Routh-Hurwitz criteria method. Routh-Hurwitz criteria. Routh-Hurwitz criteria. So whereas relative stability means it is a degree of the stability which gives complete information regarding stability. The absolute stability will give only yes or no information regarding the stability. Whether it is stable or not, it will give the information. But when you come to the relative stability, it gives complete information regarding the stability. That means the degree of a stability. It gives complete information regarding stability. Complete information regarding the stability. That means it is a degree of stability. It is a degree of stability which gives complete information regarding the stability. So example for these relative stabilities are root locus technique, Bode plot, polar plot, etc. So these are related to stability criteria. So always stable system, conditionally stable system, marginally stable system, absolute stability or relative stability. So these are important for short answer questions.